So, we had discussed integration of continuous functions and what the ideas of Newton and Leibniz. We have done pretty well, actually we did a lot of stuff. We will do more about those things later on when we will talk about indefinite integration, but now how to move beyond continuous function. Continuous functions are bounded, but every bounded function is not continuous. As we have shown an example of a step function in the last class, whether we can define anything called an area under that. So, this work was first move from continuous to bounded function was achieved by a very famous mathematician of the 19th century, George Bernard Riemann. In fact, his birthday falls on September. He was born on 17th September 1826, I would say, or 1826 or 24, something like that. So, George Bernard Riemann was a German mathematician, and he was brilliant enough to study in one of the most famous places of mathematics of all times, and especially during those times, Göttingen. Göttingen was famous because not only it hosted some of the greatest minds of the 19th century, mathematical minds of the 19th century, but it also hosted Carl Friedrich Gauss, who was called the Prince of Mathematicians. Please understand that Riemann was a very homesick child. He couldn't stay too much away from home. He used to go back to his home pretty often. And during his PhD days, his supervisor was Dirichlet. So, his PhD thesis was titled the following. Translated to English, it simply meant, what is the meaning of So, he was thinking beyond Newton and Leibniz. He was not bothering about whether a function is non-negative or not. He was just asking this following question. So, what did Riemann try to do here? What was his idea of the integral? He obviously knew what Newton did and the limiting sums that we had written, but in the last class we wrote took a positive function and built up the rectangles and wrote the sum of the area of the rectangle and took a limit as the number of points kept on increasing. So, the maximum size of the intervals decrease, and hence the limit, if it exists, is the integral, is the area actually. So, integral become a symbolism of area. Can we take out the integral from that symbolism of the area? Is the integral has a standalone meaning other than area? That is the question. So, for that he considered f to be a bounded function. F he considered a function from AB to R, and f is bounded. Remember that every continuous function is bounded on a closed and bounded interval, but every bounded function need not be continuous. Now, of course, he didn't bother much about what was the functional sign. Function could be like this, does not matter. So, what he did was to look at this interval AB and divide it. He put some partitions inside, right. What he did was he divided the whole thing into some partitions. So, I put A equal to x0 and x1, x2, x3 and xn minus 1 and b equal to xn. This is my partition. So, what is a partition P? It is a collection of points a equal to x0, x1, xn minus 1, xn equal to b. That is simply the meaning of a partition. So, that is how mathematics progresses. From one concrete idea of an area, you are moving in a direction to free the idea of the integral from the area, and you want to say that okay, if the function is non-negative, then the integral equals the area, right. Now, what Riemann did was to choose a point in this interval, say first interval x0, x1, didn't matter, you could choose it here and say choose I1, here I choose I2, you need not be in the interior, it could be any of the endpoints also, I am just writing in the interior. Xn and so on and so forth. That is how we chose, right. So, this partition, when you have chosen some point, is called a tagged partition. So, what he chose was a tagged partition, and he constructed the sum which we call the Riemann sum, which later on became famous as the Riemann sum. So, this is known as the Riemann sum. Riemann sum as per the partition. Riemann is not only famous for his integral, he is famous for his geometry, he is famous for his Riemann hypothesis, which still bogs the best mathematicians of the world. So, this is a Riemann sum, and this is nothing but the area of the rectangles which you construct with the height being f of xi I, right. So, these are rectangles you construct here. So, whatever with the function you construct a rectangle, it could be this direction, it could be in this direction, does not matter. So, there could be some cancellations of plus minus also, does not matter, it is just a Riemann sum. So, what Riemann defines, so if you take the limit, now there is a concept called, so if I keep on putting more and more points, that is as n tends to infinity, then if I take the limit of this, and if the limit exists, sorry, not infinity, it is n. So, n goes to infinity. So, number of points in the partition increases, and this, if the limit exists, we call this the integral of fx. This is the definition of the integral as per Riemann. Now, you can make it look much slightly more different. For example, if you take a partition P, P, then call the norm of the partition P, right. Call the norm of the partition P is the maximum of the length. So, maximum of xi minus xi minus 1, I varies from 1 to n. So, it is the maximum of the length of the partition. So, you can keep on choosing. So, if you have n points, you can call the partition Pn. If you have n plus 1 points, you can call the partition Pn plus 1, and so on and so forth. So, this can also be defined as limit norm Pn tends to 0, that is, as you put more and more points in, that is, as you increase the number of n, this length would keep on decreasing, this norm Pn would keep on decreasing. We take this is the same as what we have written here. So, some people can also write, some authors also want to write in this fashion, the Riemann sum. But is this the way we really study in our books? The answer is no. Go to any book, you will see something else. They talk about upper sum, lower sum, etc., etc. But Riemann didn't use any notion of upper sum and lower sum. What Riemann did, what the things that we learn in the books is the approach to Riemann integral due to Gaston-Darboux. So, Gaston-Darboux's approach to Riemann integration. So, this is exactly what you will learn in books. What Gaston-Darboux did. I don't remember offhand the life and death dates of Gaston-Darboux. Riemann died quite young and near the age of 36 or 37. Gaston-Darboux, on the other hand, was quite a famous French analyst. He did other work too. So, there is some, Gaston-Darboux is not just known because he did some modifications or did provided an easy approach to the Riemann integration theory, but he was known for something else. So, that is some, I want to celebrate Gaston-Darboux's famous result. I am sure you would enjoy this. Now, we have learned the intermediate value theorem. We have learned that, okay, let f be a continuous function, and if continuous function from a b to r in f of a is strictly less than r and f of b is strictly bigger than r, and then there is a c between a and b, there is lying in between a and b, not equal to a or b, so that f of c must equal to r. That whatever be the values that lie between f and fb, there is a point on the interval ab which will take, so whose function value would exactly equal that. That is called the intermediate value theorem that we have already discussed earlier. Now, suppose I have a derivative, I know the function is differentiable, and I know that say f dash a is strictly less than r and f dash b is strictly bigger than r, and is there some c such lying between a and b such that f of c is equal to that r. So, this thing was not known because I have not assumed the derivative to be continuous. If I do not assume the derivative to be continuous, how can I apply the natural question is how can I apply the intermediate value theorem? But Gaston-Darboux used an elegant approach and he proved even if you do not have continuity of the derivative, you still have the intermediate value theorem. So, it is Darboux's, just for a little bit of just a side tracking of, basically we are taking a little detour. Sometimes when you take a journey, you get into some by-lanes and try to discover what is in there. So, Darboux's IVT for the derivative. So, it is a very simple thing, you just take two lines to prove it. So, you have a function f from ab to r which is differentiable. Assume that the function is from r to r, but we are restricting it from ab to r, and assume that it is differentiable, that the derivatives are there, okay. And f dash a is strictly less than r and f dash b is strictly greater than r, then there exists a c element of ab such that f dash c is exactly equal to r. We have not assumed the continuity of the derivative. Of course, f would be continuous because it is differentiable. So, how would you prove this little fact? Now, consider a function gx fx minus r x. Now this function gx is differentiable because the function f is and r x is obviously a differentiable function. Now what we can immediately understand is that f, right, so this f is a continuous function, so g is also a continuous function, and so g, the function g, being a continuous function on the interval ab, right, would have a maxima or minima in that. It will have an upper bound and a lower bound, and the bounds would be attained. So there exists C in AB such that GC is equal to the minimum of G x over x element of AB. Okay. Now, what's happening is that once you, so you know this, so you know that g dash c, because it is differentiable, it is 0. So that would immediately imply f dash x, f dash c minus r is equal to 0, which will immediately imply that f dash c is equal to r. And you know that f dash of a is strictly less than r and f dash of b is strictly less than r. So that would immediately imply that c must be in AB, and that is the proof of the Darboux intermediate value theorem. So again I want to repeat that though what we are going to learn about Riemann integration is not really Riemann's story, but in the books that tell you the story that was written by Gaston Darboux, and this is one of the most famous theorem that Darboux proved, which even eluded Cauchy, that if you have a differentiable function and the derivative behaves like this, then there would be an intermediate point for which f dash c would be equal to r. So this is called the intermediate value function for a derivative, but you do not need the continuity of the derivative. This is a very important result. So we have just taken a little detour. So this is a additional information. So now we will go back. So this is what you have seen. This is what is written. This is what Riemann did, right? Now we are going to write the story of what Darboux has done about Riemann integration, how Darboux viewed Riemann integration, and in fact he proved that taking the limit, approaching the limit of this is same, the value of the integral that is obtained by this and the value of the integral that he obtains by his approach are the same. So that we will not prove that theorem, but write it down. So let us write it down here. I hope that you do not mind me rubbing of the intermediate value theorem, because this was just a detour on our journey. So again take any partition P between A and B. So you are partitioning A and B. Now what is happening is that for between every partition x0, x1, x0, x1 is the interval. So basically the partitions are of this form. So in each of this interval the function is continuous and hence would have a maximum value and a minimum value, and that is what we are going to exactly use. In fact we will not call a maximum value or a minimum value, we will call a supremum value and infimum value, because the function is not continuous, it is bounded. So it could be that there is a discontinuity, but the bound is there, right. So for example it could be like this. So it is here. So on this interval, on this particular interval, the function is bounded by this value, but the function never achieves this value. So that is what I am trying to say. So we will just use the letters Mi is equal to supremum of f x such that x element of xi minus 1 and small mi is equal to supremum of fx x element of xi minus 1. So, all these results that we are going to write down are very standard in the literature. They are in innumerable textbooks, whatever textbooks you open it will be the same thing. But we will, sorry, this would be infimum, sorry I made a mistake, so obviously this is the upper bound and the lower bound, there will be a bound because the function is bounded. Please understand our function, this is a standard assumption when you do Riemann integration. I am not talking about any other class of functions, right. So keep that in mind, we are not, so bounds are always there. So this is the bounds. So once I have the bounds, this allows me to create what is called the upper Riemann sum and the lower Riemann sum. And the upper Riemann sum, so for a given partition P, the upper Riemann sum UPF or UFP, whichever I would, there are many ways to do it. I would rather follow here the notations from Spivak and the results from this famous book by Spivak which I was telling. So he does it right, it's at UFP. So I'll just follow that in case some of you just see Spivak. But I wish this book has an Indian edition and people could, our students in our country should really buy and read this book. But anyway, these all these descriptions that I'll give is very standard. It will be found in almost all books dealing with calculus. UFP. So given the function and given the partition, the upper sum, this is actually in the literature some people call it the upper Riemann sum, but actually it should be called the upper Darboux sum. Because when I read it, when I was a graduate student, I was told that this is called the upper Darboux sum. It doesn't matter, if you replace the word Darboux by Riemann, it is also accepted in the literature because ultimately you are talking about the Riemann integral. Now this is nothing but summation I is equal to 1 to n mi xi minus xi minus 1, and the lower Riemann sum or the lower Darboux sum, I will write it as the lower Darboux sum, so you can immediately understand that mi should always be less than capital Mi, small mi should be always less than capital Mi. So one result about the nature of the Riemann sums or the Darboux sums is clear, that for any p, the lower Riemann sum is always written lesser than the upper Riemann sum. Okay. Now, how do you define the integral? The integral is defined as follows. Now, let me tell you, we are not talking about areas anymore. We are just giving a mathematical definition of the integral. Also, I am removing what Riemann had actually done and we will follow Darboux's procedure. At the very end of the lecture on when we have studied enough of Riemann integration, we would in the Darboux method we will show or at least write down the result which is also due to Gaston Darboux, which says that his approach and Riemann's approach are the same. So they integrate the same class of functions. So what does this mean? What can we do about it? There are certain issues that has to be settled beforehand, that what we want to prove that, so P1 and P2 are any partitions, then the lower Riemann sum is always bigger, lesser than the upper Riemann sum. It doesn't, if you can change P1 or P2, it doesn't matter. You can change them. You can interchange P1 and P2. It has got nothing to do with this. So, we have not even defined the integral. We are trying to understand the nature of the upper Riemann sum and the lower Riemann sum. Of course, this is the same type of area when we have studied the ideas due to Newton and Leibniz, that we are trying to press the area between the upper rectangular sum and the lower rectangular area, but that is beside the point. That is how I would ask you not to think about them in areas. Just think that these are some sums, these are just sums which are defined like that, and it does not matter whether mi could be negative, this mi could be negative also, it does not matter. So first result that we want to show is that if Q contains P, so a partition Q contains P, that is P has at least one more point than Q, at least one more point, it has more points. So all the points of P contains, all the points of P are contained in Q, then you have, then it would imply that the lower Riemann sum is less than So I just want to mention that I am using the book by Spivak, Calculus by Spivak. So I am using a symbol because otherwise I usually write UFP, UPF. So that doesn't matter. So what am I supposed to do? How am I going to prove this fact? So first step is just an induction procedure. So the first step is to take P as x0, which is A, x1, xn, right, A, and this is B. So take Q to be x0, x1, xi minus 1, t, xi plus 1, xn. Just one point more, just one point. So in between t xi minus 1 and xi, I just added one more point t. So all the points of P are also in a partition of T. Now what would happen? So what is your LPF of Q? LFP, right? LFP you know is of course summation mi xi minus 1 I is equal to 1 to n. And what is LFQ? That has to be now thought about. Now here I have two partitions to be now added, xi minus 1 to t and t to xi. Now the minimum over, so xi minus 1 to t has a minimum also, but that minimum is bigger than the minimum over the whole interval. Similarly for this interval, that the minimum here is minimum over the big interval or equal. So LFP has something like this, Li is equal to 1 to, you come to this point, 1 to I minus 1 mi xi minus 1 plus m, so I can say m dash I, you could put k also in this place, maybe I should put k, it is much more easier to understand, k minus 1 and mi dash t minus xi minus 1, right, plus m I double dash xi minus t. So what is happening? So, if I write down this whole thing and then this plus the remaining terms plus summation mk x k minus x k minus 1, k would vary from what is that point? Now, next I will have t plus 1 to n. So, this is the Riemann sum. Now, this particular term here in the ith case, it will become mi into xi minus 1. So, if you just take a fixed leaf from here and you just look at the ith interval came here, then it will be xi minus 1. Now, for that case I can replace this as mi into xi minus t, I can replace this as xi minus t plus mi into t minus xi minus 1. But you know mi, by the very definition, mi is less than mi double dash xi minus t plus mi dash t minus xi minus 1. Yeah, sorry, this is I plus 1 to n, right. So, what is happening? So, this term here is bigger than the ith term here and the remaining everything remains the same. So, immediately you will see that this term, that LF, so this term is bigger than this term. So, this immediately holds. I would leave the rest of the part for you to prove this part, and then what you do. So, suppose I have for P to Q I need to add say 20 points. So, just keep on adding 1 point and just keep on writing down the results and finally you will reach P. So, I am not doing it in detail because time constraints are also there in this course. So, once you get that, now f is a function which is bounded on AB, that is the standard thing. Now, how do I prove what we had started to prove, that okay, if I take any two partitions, what am I supposed to do, what am I going to get? Once I want to prove now this, once this is established, how do I prove this? Let me see, how do I play the game? The game is simple actually. Now, once you have a partition P1 and P2, construct a partition P1 union P2. So, this P1 union P2 partition, which we are now calling P, contains all the points of the partition P1 and all the points of the partition P2. So, L f of P1 is less than L f of P, and which is less than U f of P, and U f of P obviously is from this is less than U f of P2, and just connect these two inequalities and you are done. So, it is just a application of these two. So, once you know this, the remaining thing is very simple. What does this result allows me to do? So, here is a powerful idea. What does this is Darboux insight, that this is a true mathematical insight. So, what does this result allows me to do? This allows me to define the Riemann integral. By the way, we would take around 4 lectures to complete Riemann integral and 1 lecture would be on its generalization. So, that is the plan, and then we will get into this applications and all this stuff, improper integral and all the other issues, how to calculate indefinite integral, some important things, applications, all these things would come after that. So, now what does it say? So, for any P1 and P2 which are partitions of AB, so what I have, L f of P1 is less than U f of P2. Now, if I fix my P2, I can vary my P1, it does not matter, this relation is always holding. And suppose I fix my P2 and then I vary my P1, so P is the set of all partitions. So, it is a set consisting of all possible partitions of AB. Of course, this is a countable set. You can have 1 point, 2 point, 3 point, 4 point, 5 point, whatever. So, for fixed P2, let me write it down once. It's for fixed P2, LFP1 is less than UFP2. So, what does it imply? UFP2 is an upper bound of the set of real numbers, the set L F P, P element of this set P, right. So, if it is an upper bound, there must be a supremum. So, what supremum is the least upper bound, it should be less. So, supremum of L F P, if P belongs to P, is obviously less than U F P2. Now, this P2 was chosen arbitrarily, it does not matter. Whatever P2 I choose, I can come to the same conclusion. So, supremum of this thing acts as a lower bound to UFP2 for all P2 belonging to P. So, which implies that, so from here I will prove that supremum of LFP, P belonging to P, is less than infimum of UFP, P belonging to P. Okay. So, this is the nature of the Darboux sum. So, Darboux says that if equality holds between the two, then the common value is the integral. So, supremum P element of P, LFP, it is called the lower Riemann integral, sometimes written like this. This is just fancy thing, you just don't really, I don't really prefer writing such things, but P element of P, UFP is called the upper Riemann integral. And some people write, okay, the lower Riemann integral is always lesser than the upper Riemann integral. If they are equal, we call it the Riemann integral. So it is nothing, Darboux has defined it in this way. If these two values are equal, then the common value is defined as the integral. So, if sup P element of P is LFP is equal to inf of UFP, P element of P, this happens, if they are equal, then their common value is the integral. This is the integral according to Darboux, and he says that this is the Riemann integral. But to us at this moment, this is an integral for a bounded function defined by Darboux. At the very end, but Riemann did something else in his thesis, and I wrote down in the very beginning that name of the thesis was what is the meaning of integral a to b f x dx. It was his thesis in 1854. Now, then we will at the end, we will write down after in the end of the next class as the Darboux's main theorem, which shows that Riemann's approach and his approach are same, right. So, what Darboux also showed that if you take the limit, we have defined what is called the norm of the partition, right. If you take LFPN limit with norm Pn, I mean here is the partition with n points, right, and the largest interval, length of the interval of the partition that goes to 0, sorry not infinity. It simply means n tends to infinity, nothing else. It is a fancier way of writing n tends to infinity, but sometimes mathematicians want it to be more geometrically visible. This is what Darboux proved. Darboux proved that not only this is true, this is actually true. If the Riemann integral exists, if this integral exists, if this is true, if this holds, then this also holds. So, with this we end our talk here. So, we have just introduced the Riemann integral. So, we will not get into too much of what Darboux says and what with these things will come at the end. And so, this integral is actually this integral. Darboux says that if this happens, then this must also happen. And this is exactly equal to the Riemann sum. That is what Darboux would prove. That is Darboux's one of his another famous theorems. Now, what we are going to do in the next class is to introduce examples showing how to calculate integrals, what is the necessary and sufficient condition for an integral to exist, which is nothing but which is a very clever restating of the definition. So, that is also Darboux's theorem, and that actually helps in really finding a Riemann integral, really showing that a function is Riemann integrable. So, we will do that in the next class. Thank you.